So you can get the same answer. So the values are stored in Python, run with the Python and can get the result. So the per unit value here, coding, whatever thing you are given in the book or anything, just type it. So the given data, formulas and print the value. Which value you want, you can print it, you will print here. So these are the per unit value, fault calculation, difference, next symmetrical component. So symmetrical component. So already it's about VA/VB phasor component can convert it into sequencing component VA0, VA1, VA2, and you can use the result like this. So you can convert. So here positive sequence voltage, sorry, zero sequence, positive sequence and negative sequence having three values, VA0 or 1 magnitude angle. Similarly for VA1, VA2 and VA0, for three component values are displayed here, 1, 2, 3, 1, 2, 3, 1, 2, 3 for VA0, VA1 and VA2. Voltage, current level, symmetrical value, component values, next fault calculation, current VA/V1, so positive sequence current, symmetrical component are there. So here just we are going to type the equation, giving the value for that, running the program, you are seeing the output. So this is the basic thing. Whatever you are calculating in your book or refer in your book, you can easily do it and run it and get the output. That's a simple one. Then you can go for this is a spider ID. So here you type the codings. So here you can view the variables, run it. If you are pressing the green button, it will run and give the output result here. So this is spider. Similarly IDE on the Python IDE for power system analysis tools. Other tools also there. Pipe power and quantum powers are there. These are two tools you can run load flow analysis, short circuit studies and everything you can do it by using these things. I give you some example for power flow using grid car. So here I am taking a 30-bus system, IEEE 30-bus system, open it, here, power flow time series, short circuit, voltage plants and optimal power flow for time series and everything there. Consider so the values also you can see. Now you are running a power flow power flow voltage magnitude values for each buses, power, current, branch loading and branch losses also there. So this is a graphical tool developed in Python. So it gives the entire details about the power flow studies. And you can go for short circuit also. You have to make some more changes in that, and you have to do. I have not done that one. So here the short circuit studies also there. This one. Sorry. This one. This is short circuit calculations. So one more thing, you can go for network analysis. How is that about network analysis in power system? We are having 30 bus system, 33 bus system, everything are there. You can analyze the using network analysis. You can get the output. Just taking a 4 bus system. It's a simple program. Import power pattern up to this one import. Just I call a function. So it runs the power flow and give the output result. So these are 4 buses, 4 nodes, bus voltage, line loading. So the graphical represent from 0.9 to 1.9 voltage. And voltage, each buses, the voltages are given in color. Color means if it is a blue, it nearly 0.9. If it is a red, it above 1. Given in colors. Similarly for current loading in branches. Green color, it's nearly 60% loading, and light blue color, nearly 40 or 45% loading. So you can get the result in graphical format, and the voltage of each buses and the current you can easily identify. It's given for 4 bus system. You can apply for n number of bus systems. So this one for 24 bus system. So this is 39 bus system, and it will go up to 6,000 bus systems also there. The 1,888 bus system. So similarly, you can find out the voltage and line loadings in this one. Next, we can go for fault problem. So unsymmetrical fault. So madam already explained about the symmetrical component. So you can convert this unsymmetrical to symmetrical by using symmetrical component. So first madam has explained about the per unit. First unit we already done the per unit studies. So calculation of per unit everything. Second unit, in the first unit of itself, you have to draw the reactance diagram. So these two are very basic and very important for first unit. So next, for second unit, load flow, and the third unit, load flow, you are going to know the load using Newton Raphson method, Gaussian method, flow chart algorithm, and problem solutions you have to find out. In the third unit, symmetrical component, symmetrical fault analysis, and bus building algorithm in third unit. Fourth unit, unsymmetrical fault analysis using symmetrical component. Symmetrical component is nothing but positive, negative and zero frequency, and it will be used for finding the fault current for line to line, line to ground, double line to ground, line to line fault. So here you have to draw the equivalent diagram and solve for the problem. So here I am giving one solution. So line to ground fault. So here line to ground fault, voltage diagrams x1, x2, x0, that is positive, negative, zero sequence impedance in complex format. So I1 current. So IA1 positive sequence current equal to voltage divided by zero sequence, positive sequence and negative sequence. It's a border current. That's why x0. So IA equal to 3 IA1. So you can get the values multiplying this IA with 3 IA and IC value E by x0 C equal to IA divided by IC. So the ratio of the line to ground fault of three phase fault is equal to 1.286. So you are substituting the value, you can get the 1.286 for line to ground fault. Next line to ground fault, line current. It's the line current, IA current. Next line to line fault, x1 equal to, so equal to 1, x1 equal to x2, because here you don't have x0 because there is no zero sequence in line to line fault. So x1 and x2 are not there, so the complex values are taken. So IA1 equal to E divided by x1 plus x2, so this is the formula. So you are including the pi, cos, sin. For that you have to include the math library for running this pi, cos and sin values. So A equal to complex cos j sin, that is cos theta plus j into sin theta, that format. And get here the angle is given, here P1 and PI, that is pi 125 by 180, 120 pi divided by 180. So B equal to A square, IA1 equal to, that is what is A. A you already known that the values, complex value, A square, the negative of that value. So IA2 equal to minus IA1. So IA equal to B minus A into IA1. IAP equal to E divided by x1. So C equal to IA into real divided by IAP into imaginary. The ratio of the line to line fault of three phase fault equal to value is 0.866. So three phase line to ground fault. Here x positive sequence, zero sequence and negative sequence of the impedance are given. Here 0, you don't have any real part, only imaginary part there. E equal to 1, always taken 1 per unit voltage. So IA equal to 3E divided by x1, x2 and x0. IA equal to IA into imaginary part alone taken as IA. IA0 equal to IA by 3, IA1 equal to IA by 3. These are given in the formulas. We have taken these values from the formulas. IA2 and everything, these are taken. IG1 equal to IA0 plus IA1 plus IA2. IG2 equal to IA1 plus IA2. IG3 equal to IG2. So C equal to IG1 divided by IG2. A equal to round off. So you are making a round off. C and D values are there. So printing the ratio of the contribution of generator 1, 2, 3, C, D, D. So the values, printing the values. So I3 equal to E divided by x1, I1 equal to 3E divided by x1 plus x2 plus x0, y equal to I3 by I1. So the ratio contribution generator is 10.125, 4.05, 4.05. Next, three-phase line to ground fault 1, single line to ground fault 14.3 amps. Next, double line to ground fault. Here, the voltage is taken as 1, R equal to 1250 equal to 3, V equal to 600. So, from we are importing the math library cos, sin, pi, square root, A tan and impedance values. A equal to e power j 120 into j, that one. This cos 120, sin 120. B equal to A square, the negative values. Here, so IA1 equal to V divided by x1 plus x2 power minus 1, x0 power minus 1, whole power minus 1, IB is only 1200, EA1, IA2 equal to VA1 divided by x2, I0 equal to VN by x0, IA equal to IA0 plus IA1 plus IA2, IB equal to IA0 plus B into IA1 plus A into IA2, IC equal to, that is nothing but IABC equal to sequence component, the transformation matrix into IA1, IA2, IA3, first zero sequence, positive sequence, negative sequence, correct? So here IA0 are real values, imaginary values, and the square root of adding these two values, square of IA real plus square root of imaginary, IA real equal to this imaginary value. Similarly for B, square root of B value, similarly square root of C value, IAB equal to A tan of IA1 divided by, imaginary divided by real. This gives the angle. So which brings fault current for double line to ground fault to 26,011 and different result due to calculation in the textbooks. So these are the line to line, line to ground and double line to ground faults are given here.
How many buses?
So this is not bus, just given the voltage. This one is not taken for just ground, double line to ground fault. Three-phase system, double line to ground fault. So here I am not taking any bus, this one. Just I am calculating the three-phase fault in the line. That's all. Similarly for double line to ground fault current equal to 20,800 amps. Any doubt in Python or MATLAB related?
You showed some drawings and all.
Yeah.
So what are these drawings? Single line diagrams?
Not single line diagrams, graphical diagram. More or equal to single line diagram. It's a graphical representation in Python. So Panda Power software is there, the library is there. Using that you can draw that graph.
They are representing lines.
Yes, lines, transmission lines and the round shape are represented as buses. Here I am representing that node. Node or bus.
Single line diagram?
That also a single line diagram also.
So like
This,
I have voltage and the other side current In between I have some parameter, it is nothing but the zero sequence impedance of the three-phase element. Sequence impedance of the three-phase element. So I can say this is nothing but Z012, which is nothing but A inverse ZABC into A. A is A matrix I know. And if you give me what is ZABC, that is in the ABC frame, I can immediately find out what is the corresponding sequence frame impedance. Okay? So just like voltage and current, I can go either direction using the transformation. Okay. Now, fortunately, there are some more additional simplified information. After all, in power system, we have certain generators, transformer, transmission line, and load. In all these cases, now the sequence impedance will be a decoupled one. What do you mean by that? All the off-diagonal terms will be of zero.
Sir, if it is a generator, then you will have you don't have the same set of impedance for the positive and negative impedance. The numerator
I
is
am coming to that. If it is a rotating synchronous generator, synchronous motor, then you have Z0, Z1 and Z2. Generally, all of them will have different values. Okay? In ABC frame, there will be mutual term. See, you have A phase winding and B phase winding, there is a even in the transmission line. A phase, B phase, there is going to be a coupling. That exists only in the ABC frame and not in the sequence frame. Okay? Now, if it is a transformer, then you can additionally you can observe that the zero sequence, positive sequence, negative sequence impedances are equal, and the transmission line, generally the zero sequence impedance is much larger, and positive sequence and negative sequence impedances are equal. And for rotating machine, in general, all of them will have, all the three will have different values, but not the coupling. Coupling terms will be the off-diagonal terms will be zero. Okay? Then, what is a sequence network? I know what is sequence voltage, I know what is sequence current, and just now we said about the sequence impedance, but can you not put it in a network form? That is the sequence network. Okay? The positive sequence network will have only the positive sequence voltages, positive sequence impedances, and the corresponding positive sequence current. Similar for the other things also. So, for example, let us start with the generator. This is normally the generators we can as well assume that it is generating a balanced three-phase voltage, and it supplies a current of IA, IC. So this is the ABC frame. Okay. Now I can, as I told you, I can assume this generator voltage is EA, EB, EC. Of course, N is, when I say EA, it is EAN. Okay. So this is the voltage phasors, generator voltage phasor. Then in that case, I can write EA, EB, EC as EA is EA itself, and what is EB? It is square halfway by A square. Then I get A square times EA, it is nothing but EB. Similarly, EC is A times EB. So I have not done any operation, just I say it is a balanced three-phase generator, and EA, EB, EC will be like this. Now, once I know that one, if I necessary, I can find the inverse also. Okay? And I have an interesting result when I go that inverse relation. That means I am now finding out the zero sequence voltage, positive sequence voltage, negative sequence voltage, corresponding to the phase component. Just now what I mentioned. 1 A square A, 1 A square A. So this is the phase sequence voltages. And when I want to find out the corresponding sequence voltages, I have to make use of the property 1 plus A square equals 0 like that. So if I multiply these two, I have a relation like this, which has got effectively as 1. That means I have a voltage, generator voltage at the positive sequence, but there is no voltage, generator voltage at the zero sequence as well as the negative sequence. Okay? So I have a generation voltage only at the positive sequence network. Okay, now I take I consider the positive sequence network of the generator. When I say positive sequence network, I have current as I1, IQ1, IC1 like that, and I have the Z positive sequence with Z1, Z1, Z1. Now, what is the total of IA0 plus the summation of these three, IA1 plus IB1 plus IC1, that must be equal to 0. So all the three are equal in magnitude and displaced by 150 degrees, so that is going to become 0. That means at this point, if Kirchhoff's current law is applied, this current is going to become 0. That means there is no current in the neutral. Okay? When there is no current, this point and this point are same potential. So now what I can do is, I can go for the single phase representation of this one, and that is this one. This is the voltage, and this is that one, and this is the terminal. So the current is IA1. Okay? And this is the generator voltage, and this is the terminal voltage. I can simply say this generator voltage minus the drop. Z1 into IA1, that will be the terminal voltage. So what is this one? This is nothing but the single phase representation of a generator. Okay? Now, before we change over the slide, can you imagine how the negative sequence network for the generator will be?
You don't have the source. You will not have the source because
Yeah, that's good. That's good.
sequence.
Okay. There are two things. One, there is no source to be here, and Z1 should be replaced by Z2. Okay. Then I get the representation for the negative sequence diagram like that. Then for zero sequence network, it is slightly different. Zero sequence current, IA0, IB1, IB0, IC0. Now if you look at the zero sequence component, they are equal and they are in the same phase. So if I apply the Kirchhoff's current law at this point, the outgoing currents are IA0, IB0, IC0, all of them are equal. So 3 times IA0. So naturally this current should be 3 times IA0. Okay? So previously there is no current in the neutral, but now I have current at 3 times IA0. I want to take this into as account to draw the single phase equivalent. How do we get that one? Strictly speaking, by looking at this one, the single phase circuit will be starting from this one like this. But there is one problem. Here the current is 3 times IA0, here the current is IA0. How I can draw it? So you see which one of the currents are different. So for that one, a small adjustment. This could be taken as 3 times Z passing through a current of IA0. Okay? So that is the reason why I multiply by the grounding impedance Zn by 3 times Zn, and this is Z0. And this total, I call it as zero sequence impedance of the generator. And the current is. So this is the positive sequence network for the generator, and this is for the negative sequence, and third one is for the zero sequence. Representation of the generator. Okay? Now we are ready to take up the positive. These terminal relations I think is quite simple. Okay? The terminal relation that just indicated, for example, EA1 is EA minus the drop. Like that I can draw it, I can write the terminal relation like this. Okay, the negative sequence, there is no voltage, and similarly for zero sequence also no voltage. So only the drop. So these are the three equations for the terminal voltage. Okay. The only thing is, now we are ready to draw the sequence network. Particularly the zero sequence network requires a greater attention, unlike in case of positive sequence and negative sequence. Why it is so? We used to say it behaves as a DC circuit because all the three IA0, IB0, IC0s are equal. Okay, and if you need it, I will give some more explanation. So zero sequence network for a three-phase load, for example. This is a three-phase load. Okay. Now, when a current flows through that one, naturally I think I already told you the importance of Zn becomes 3 times Zn. So this is become three-phase, the single-phase approximation for the load. Even at this point itself, I can also say, suppose if this neutral connection is not there, neutral is isolated,
There is no power.
then
There is no path for
there is no path for the zero sequence current. So there will not, that I have indicated by a open circuit. I have indicated by a open circuit. How about this one? Delta. Delta connected again, it will circulate in that winding but not outside. If it is a 10 amps here, 10 amps here, 10 amps here, what is the current here? 10 amps coming here, 10 amps going here, this current will become zero. So as per the light, there is no current, but in the winding, there is a possibility of circulating current. Okay? So that is regarding the load. Now coming to the transformer. Transformer, I can have different star, delta, and star set, grounded, isolated, all combinations. Okay? The transformer, you know what? The primary will carry current, only the zero sequence current, I am talking about that. Only when the secondary carries current, when there is a current in the secondary, and then there must be a path for the zero sequence component of current. It's very simple. There are only few cases. Okay? What you could do is, you can segregate it by putting a two dots here and two dots there, and you can properly connect them to indicate the various combinations. Okay? For example, first case, delta delta. Yes, sorry. Okay? The transformer, we start with this one. Star. No problem. Now this is also grounded. So star means now the zero sequence component current will come like it and then come like that and goes down. So there is a complete path is there. So I can represent it with this. This side also there is a provision, so I connect this one. And second side also I got provision, so I connect that. I will follow the originally you start with this one and like this. Then you connect them depending upon whether there is a path for the zero sequence current or not. Okay. So in this case, yes, I have path at both sides, so I can actually connect them. Now let's come here. This is isolated, ground isolated. That means zero sequence current cannot flow through that. Just now what we believe is primary I cannot have current if there is no current in the secondary. Okay. So now this one I can make it open, and this one I close it because in case if there is a path, return path provided by some other component, then it may carry current. To indicate that one, I connect it and leave. Otherwise, you can also say this is hanging. There is no current through this transformer now, as it is. That is what I intend to make it. So this is for star relay. And how about the impedances? How do I get to take care of it? What is Z0? It is the zero sequence impedance of the transformer plus 3 times this one plus 3 times this one. That must be equal to Z0. Catch? The transformer will have its own zero sequence impedance, and the grounding, there are two grounding impedance I should multiply by 3 and then I have to add. Okay? Now I think this I can explain. Similarly, delta, it can only circulate, so I can indicate it like that. And here it is again, if there is going to be path provided by some other component, yes it may. Otherwise, if there is a circulating current and the corresponding primary also will have current, that will be indicated like this. Okay, now I have various combinations. What we can do is, if I have a power system like that now, it's a very small system. A generator and 2 motors and 2 transformers and 1 transmission line. Transformers are connected in a different manner and the generator also motors. Now I may like to draw the zero sequence network, positive sequence network and negative sequence network. Positive sequence network is the most simplest one and it is exactly same as the per unit impedance diagram what you might have taught earlier. So positive sequence impedance, positive sequence network, it is same as the per unit impedance. Then the negative sequence, zero sequence, what's the difference now? Negative sequence, there is no voltage generated because we already proved that generator will not have negative sequence voltage. So that has to be taken into account. And zero sequence, again no generator voltage. Apart from that, zero sequence network depends on the transformer connections. So these things are to be taken into account. Okay? It's not at all difficult. I will definitely say it. For example, in this system, for this one, you can measure a parameter. These are the parameters. Because I already told you how to combine these two, multiply by 3, add to this one, that will be the total zero sequence impedance. So like that, different component I have. First thing is, it's better you draw the positive sequence network. Positive sequence network. Just now I told you that it's same as the per unit impedance diagram. This is generator reactance, and a transformer, and a transmission line, another transformer, and there are two motors. I'm sure that all of you are quite familiar with drawing to put the proper values, that's all now. And since all the reactances are given, I get J everywhere. So I quite feel comfortable of this one now. So how it is going to be negative sequence? No voltage sources will be there, number one. Number two, the positive sequence and negative sequence value may be different at some point. If that being the case, you properly change it, that's all. Only for zero sequence, you are using little more careful. So always start with the positive sequence, then draw the negative sequence, then zero sequence. Okay? So this is the negative sequence. You could catch the photo. This one, try to remember this structure and this structure is same except for the voltage source will not be there. That's all. Okay? And for zero sequence, you have to be more careful. Zero sequence, there is a transformer start at the second side, so that has to be closed until delta, so if at all, the circulating current will be there, that would be indicated like that. Like that same principle what we have. So I can draw the zero sequence network also. Okay? Then using this, now we are ready to solve the unsymmetrical fault occurring at the generator terminal. By doing that exercise, you will gain more confidence, so you can extend it to fault occurring at any point in a three-phase system. Okay? This is something I always used to say, the baby has to crawl before you start walking. Okay? So first try to understand the simple case, then you can extend that one for the next higher level case. Okay. These are the three terminal relations which are true for all types of fault. That's only terminal relations. From the diagram what we are already seen. Okay? And depending upon the type of fault, unsymmetric fault can be single line to ground fault, line to line fault, double line to ground fault. These are the three unsymmetrical faults. Okay? And the fault will specify three more conditions. This is the general one what I have. These are the three general equations. Apart from that, for each type of fault, there will be three equations will be there. And there will be in terms of these components of current and voltage. I will explain it now. Then that one can also be converted into the sequence component expression. Phase component expressions, the fault condition can be transformed to the sequence component. Now, I have to solve that one for the current IA0, IA1, IA2. Because the moment I solve for IA1, IA2, IA0, if necessary, I can as well find out the terminal voltage from these three equations. Because these are the parameters, so if I know the current, then I can calculate the terminal voltage. So greater concentration can be given only for the current. If you try to imagine that there are 6 equations and 6 unknown, then the solution part is going to become difficult. Strictly speaking, there are 6 equations and 6 unknown, but do it in a systematic way. Don't try to imagine. If If you ask any mathematician, they will say, oh, you have 6 equations, 6 unknowns, you solve it. But you have to use your shortcut method. Don't try to do it like that. Try to make use of the fall condition and try to find out what it is IA1, IA2 or IA0. The moment you have that one, then the terminal voltages can be obtained using this equation 16, 17, 18. Now what is the part of this transformation can also be done? A single line don't work. Just do it for the 2 detail for one and then we have to skip that one.